I'll go ahead and get us started. Oh, nice day here. Maybe we'll kind of close it up though so we don't have the glare. Gonna warm up to a nice day. That's good. Hopefully though it will rain all weekend and all spring break, so all you want to do is study and then return back with all your homework all caught up and rested and ready to go. I think that's actually kind of nice about the spring semester versus the fall semester. There's that intermission, if you will, about the time people are starting to get tired and falling behind. You get this whole week to kind of rest and catch up, and then knowing though that as soon as you return, you're going to hit some of the hardest stuff of all of your classes, and so that kind of gets you through to May. And once you get into May, then you kind of see the light at the end of the tunnel, and then that motivation kind of picks up again. Oh, yeah, I'm gonna make it there. So, but fall doesn't have that break. Although I guess there is that Thanksgiving, but that's a very busy time, so it's not usually quite the same effect, and it's only 2 days in a weekend versus a whole week. Well, all that said, let's jump into chapter 9, and we won't get too sophisticated, or maybe, depending how time goes here. Our math level will certainly be significantly higher than in Physics 102, but I wanted to start by saying we're about to hit the concept of momentum. You've seen momentum before. You saw it in the Physics 102. And so as I've been saying as we've been going through these 8 weeks together, and we'll continue to say for the next 8 weeks, now that we've hit the halfway point, is that the point of this class, of course, is physics and analytical and mechanics, but it grabs the mechanics, the basic principles we learned in 102, together with the math you learned in 150, and of course, all the previous math and all the previous science, so it's not just those classes, but taking as much science as you've learned and as much math as you've learned and putting them together and getting some pretty involved and complicated problems and pretty advanced. And as some of you pointed out, not perfect in the sense that we still overly simplify some problems and we ignore certain things, like you guys were talking about last time, the mass of the pulleys. We've ignored that'll change. The mass of the strings in the rope, we ignore that, and that will change too. And so as your level of education continues, the problems get more realistic, but at least at this point then we've got as far and most advanced as any of you done so far. And you might remember from the 102, I thought I'd take this as a moment to maybe keep your mind focused. Remember what I said in 102, and I should emphasize it this semester also, that if you know Newton's 3 laws of motion, and together with the 3 conservational principles, we can solve for any and all of our motions. And it doesn't matter if we're looking at a car or a train or a spaceship, we can then apply those. And so running through those again, we've already in this class done Newton's 3 laws of motion. We've already done one of the conservational principles, that was conservation of energy. And now we're about to see conservation of momentum. And then following that, we will see conservation of angular momentum, if you remember those 3 from your 102. So that's my way of introducing to chapter 9. And so obviously chapter 9 has to do with momentum. And technically this is our linear momentum. And it's simply defined this way. And I'll pause right there. Here's the momentum, the phrase, the P for momentum. It's got a little arrowhead over it, which means what? Yeah, it's a vector, so that is a level up from anything we saw in the 102. We didn't use the fancy symbol vectors. But it is the same as you saw in 102. It is the product of 2 things you already are familiar with, mass and velocity. And again, velocity is a vector, so I put the little arrowhead over it. If it helps, I like to say this. Remember then that this is really 3 or 2 separate equations. 2 if we're dealing with 2 dimensions, and 3 for those few occasions we do with 3 dimensions. But this would be the momentum then in the x direction is mass times velocity in the x direction. And momentum in the y direction would be mass times velocity in the y direction. And periodically, just to keep us on our toes and make sure we're, not missing the point, the world is 3 dimensions, and so we got to periodically say, okay, look, if you can do it for 2 dimensions, hopefully you can extend that into 3 dimensions. And so just to test you, all of a sudden, boom, here's a 3-dimensional type of problem. So the most 3-dimensional problems we've had so far, I think, have been chapter 6. That will soon change, starting now in this chapter, but more so in chapter 10, where we say, okay, let's look at our motion. So again, just starting off the chapter with a definition that, again, I think you already know. And like I said, I don't think we'll see anything here that you don't already know. Maybe a little different because we do different symbolism. We have more mathematics, and one of the mathematics is the vectors. And if you were to write this then with your, your I hat, you would say px I hat plus py j hat. And if you wanted to include it, then k hat equals then, of course, mvx I hat plus mvy j hat plus mvz j hat. And so writing it as one equation with the I, j's, and k's, or writing them as 3 separate equations is, of course, the same thing. And, oh, thank you. Thank you. K hat is, of course, that same thing. And so sometimes we do it one way, sometimes we do it the other. But again, momentum, definition, same as Physics 102. Nothing new there. How about the units then? What are the units to measure this new quantity? And I say new, but it's not really new, but new for us this semester so far, our first introduction this semester. It would be? Yeah, and so the unit for the mass is a kilogram. The unit for velocity is meters per second. And that's end of story. I mean, that is all it is. And we don't even give it its own fancy name here. I think I mentioned this before, that all the quantities starting about Newton's time with force and going forward, like energy, joules, like power, watts. We've seen those named after the great scientists in the field. But things that predate Newton, we don't, for whatever reasons. I'm not real sure, but we don't. So this predates Newton, so we don't give it its own special units. But I should point this out. You have now seen quite a few units. You, of course, have seen the meter, the second, and the kilogram. From that, we then saw meters per second and meters per second squared. Following that, we saw kilogram meters per second squared, followed then by kilogram meters squared over second squared, followed again by kilogram meters squared second cubed, and now following today, kilogram meter per second. So let's talk about each of these. We've done enough that it's worth pausing here and saying, do you remember all these? Let's go through them. I'll start, of course, with the simple. This one is M for meters, measures distance. S for seconds, measures time. kg for kilogram, measures mass. All right, so there's chapter 1. Going into chapter 2, this is what? Meters per second measures velocity. This is meters per second squared measures acceleration. All right, now we get to, I think, the ones that can easily get confused, and they're nice to see them in one big list. What's this? Kilogram meters per second squared? Newtons. And a Newton measures a force. So there is our unit for the force, the Newton. What's this? Yeah, that is 1 more meter. That is a Newton times a meter, which we called a joule. Yeah, so that's the unit of joule. And the joule measures? Energy. So what's this one? Yeah, that's 1 more per second, right? That would be then the joule and then another second. And then joule per second. And it measures power. And we call it, I heard somebody say it, a watt. Yeah. And so there's the 3 from last chapter. And now in the new one from this chapter, No new name. How boring is that? I feel like I just got to give it a name here. So we'll call it, yeah, Young. There you go. From the great scientist working in the field. Sure. But it has no name here. Although, and here's what I wanted to point out. Watch this. What if I were to take that and multiply top and bottom by the second? In other words, multiply by 1. Don't change anything. What do you get? What's that? So a Newton times a second is really the same thing. And it's good to see that, because you will see it, and it often throws students off a little bit. They say, whoa, units for momentum, Newton second. I thought you said it was a kilogram meter per second. And yeah, sure, it's the same thing. And in fact, you'll see it right away when we do a lab. I almost said next Monday, but that's spring break. But the Monday after that, when we will do a lab on momentum, and the little computer will take the data, and you'll have the little graph that we've done in those Logger Pros, and you'll see that the equipment will measure, and it'll say units of momentum, and it will have a Newton second. It won't have the kilogram meters per second. So. Well, it would be that, and then I put another second and another second like that. Now I'm going to group this together. What's this? That one. It's a Newton, so it's a Newton times a second. So a Newton times a second is the same as a kilogram meter per second. So either way, you'll see the units listed that way. And again, not too revolutionary, but I think new. I don't think we did that in 102. We just used kilogram meters per second and never mentioned about the Newton times a second. But it does come out to be convenient at times, as you'll see why. Well, again, let's keep going here. Let's take a look, or maybe I should say a relook, at Newton's second law here. You're familiar with Newton's second law this way, that the net force is mass times acceleration. Fair enough? But acceleration, going back to chapter 4, is the time derivative of velocity. Fair enough? Now, using your calculus, most of the time when you have a constant inside a derivative, you pull it forward. But couldn't the reverse work? And in this case, I have the reverse. I have a constant out in front of the derivative. What could I do with that constant? Couldn't I move it into the derivative? Isn't that the same thing? And of course, why would I want to do that? Well, hopefully that will become pretty clear as the next hour moves forward. But what do you notice when I put those together? That is our definition of momentum. And this is kind of our first clue of why it's kind of convenient to think about momentum, which is the product of two things we've already worked with, instead of looking at them separately. And so what we have here is the net force can be thought of as how the momentum changes with time. And so instead of thinking of it as mass times the acceleration, but that's still valid. I don't mean to ever say don't think of it that way. I'm just saying this is an alternative way of viewing Newton's second law, that when you are applying a force, what are you doing to it? You are changing its momentum. Okay? And here's what's kind of nice about it. Let's say that I had two different objects that I wanted to compare. Let's just say one is a bicycle over here and one is a car over here. And if I come along and I put a force on the bike and I put exactly the same force for the same amount of time on the car, same force, right? Do they move the same? Do they have the same acceleration? No, why not? They have different masses. But what could we say here looking at it this way instead of looking at it in terms of the acceleration. If I push on the bike and I push on the car, how does the momentum of the bike compare to the momentum of the car? Do you see it in here? It's the same. Now, I'll go back to the last chapters. Did these two have the same acceleration? No. Which one had a greater acceleration? The bike, because it had less mass. So over here, what you would say is I have a large speed and a small mass. Over here, I have a low speed but a large mass. And so what this is saying, although maybe I should undo the derivative and say if you want to solve this for momentum, you have to take the integral of momentum. The integral of momentum would be force integrated over time. And maybe I should put this as a change, so we go from some initial point to some final point, something like this. But this equation can be nice and very useful. So in no way am I saying forget F equals ma. Never forget that. I mean, that's probably the most fundamental, important thing you can learn in physics, and particularly this semester. So I am not saying forget this, and I'm not replacing it, but I am trying to say there is a different way of looking at Newton's second law that will be useful at times, and this is just one of many examples where it would be useful. I come along and I apply a force to a bike, and I apply that same force to the car. And that same force gives me the same change in momentum of those two objects. So assuming they started from rest, this one would have the same amount of momentum as that one. Although I guess I could say opposite direction since I'm kind of indicating one. But at magnitude, you get the idea here that I will get the same momentum. And so that's kind of nice to say that even though they're going at different speeds, and even though they had different accelerations, they had the same force and hence the same momentum. And so that becomes a nice property. And you're going to see that. Yeah?
If you applied a force that was big enough to move the bike but not big enough to move the car.
Oh, now I should be careful here. Okay, fair enough, fair enough. I really didn't draw a free body diagram, and I really didn't do a complete justice here. Let me, first of all, see if I can get a pen that's got a little more moisture to it. But notice it does say net force here. Okay? And so I think what you are really saying here is, as I look at a bike and I draw the free body diagram of a bike compared to a car, there would be frictional forces down here, and the net force would be different than just me pushing on it. And so what I was trying to imply, and probably should have said, is that what if this was a bike with no frictional force? This was a car with no frictional force. So when I push on it and then I push on it, the net forces are the same. And then if the net forces are the same, then for the same amount of time when I do this integral, they will have the same change in momentum. But you're right that in the real world, there is probably some frictional force. There is probably some frictional force. I doubt if those are the same. And hence, even though I pushed the same, the net force is not the same. And therefore, the momentum is not the same. All right, so good. I'm glad you pressed me on it, because that could lead to some confusion here. But just starting the chapter, pretty simple. I just wanted to say that force was the only force, and hence it's also the net force. But of course, as you can imagine, if there was only one force, it would be an easy problem. And it'd be a Physics 102 problem. And you're not going to see anything like that this semester. You've already seen the easy ones. Now we're moving on to the hard ones here. So ours have multiple forces, and we got to draw the free body diagram to figure out what's going on. But it does become useful in this sense. This change in momentum is often described as an impulse. And we say, look, this is the impulse you have put on the object. Now, we don't say force because it is not just force. Impulse is what? Force and time for that force. If I was drawing a graph and say, look, let's take the look at force versus time. And if we go back to the bike and car for a moment, we can come over and say, I put a certain force for a certain amount of time. And to keep it simple, let's just say it is a constant force for maybe 1 second. And as you look mathematically at that graph, here's what you're saying. Some constant force, F, for a time of 1 second. And so if you were to integrate it, wouldn't that be the area under the curve? Isn't that what you learned from your Calculus 150 class? That an integral can be represented in a graph as the area under the curve? Okay, and so the impulse is really this area. The impulse is the change in momentum. The impulse is not the force, it is not the time, it's the combination of the two. Okay? So be careful with the word when we say, okay, an impulse is applied to it. Now in this case, if I were to push this one with a force for 1 second, and the car for 1 second, the graph would look the same. And so it might look something like this for the second object. Fair enough? And same impulse, same change in momentum. But are there other ways of getting the same impulse with a different force? Could I get this bike having the same momentum as this car? So I push this car with a force for 1 second. Is there some other way I could get this car to have that same impulse? Yeah, there's an infinite number, right? I mean, think about what else could you do to this bike? How else could you get it to have the same impulse besides the same amount of force for the same amount of time? Yeah, it's a whole slew of combinations. I mean, one combination that you just said is, well, what if I did this? What if I gave it a lot of force for a short period of time? Couldn't that be the same area under the curve? Yeah. And so a short force for a long period of time could actually be the same as, what's the other alternative? Yeah, I think I'm out of colors here. Blue. I could give it a small force for a longer period of time. And that could be the same area under the curve. And so there's a lot of different combinations of how I can get to that same momentum. Okay, if this is an automobile and you've got two automobiles racing down the street, you could have one automobile that has a small force for a long period of time, or another one that's, a sporty car that has a large force for a short amount of time. They both get up to 60 miles an hour. But the sports car, it's 60 miles an hour in 4 or 5 seconds. My Yugo gets to 60 miles an hour in a half hour down the road, So, it depends on how you apply that force. So again, don't want you to ever forget F equals ma, but do want to point out there's another way of kind of looking at this that at times would be convenient here. And even though I've talked about a long period of time and a short force, I must admit, most of the time, impulses are kind of nice to deal with when you have these hard, large forces for a short moment, like a baseball bat hitting a baseball. That ball comes off, say, 90 miles an hour. Huge force, short time. But doesn't the pitcher also get the ball going 90 miles an hour? Do they apply a force as large as the bat? No, but how does the pitcher get the ball to 90 miles an hour? much longer period of time, right? It's that whole wind up. It's pulling back and jumping forward and twisting, snapping, you know, and that whole long period of time. So you can get it up to 90 miles an hour either by that crisp, large force or that long period of time. So we're going to do a lot of this probably. This is where it's going to be probably the most useful to us. Is we're looking at an object and it's force, and there's more formality, I should say, net force there. But as we look at the force at a moment of time, there's no force, no force, no force, no force, and then it gets hit. Whoa! And then no force, no force, no force, no force. Okay? And so this area under the curve can be the same as some kind of average force over a period of time. Okay? And that's what we're going to see here. So watch this for a moment. The equation said this: the change in momentum is equal to the integral of F integrated with respect to time. And by the way, maybe I should emphasize that. It just dawned on me. This is an integral of F and time. Didn't we see the last chapter? An integral of F x? Yeah, what was that? Work. So please don't confuse those. Especially coming from, you know, your Calculus 150, where you always did integrals with one variable. It was just, hey, what's the integral? What's the integral? What's the integral? What's the integral? But now, remember, when you did your calculus, you were really saying integrate that, and that little dx was not x as in position, it was an x as in a variable. That it could be x for position, but it could also be t for time, and that's what we're seeing now as we get into a physics class where we apply our calculus. And these in no way are the same thing, even though you say, oh, integrate force. Oh, integrate force. And we should be a little clearer. Oh, integrate force with respect to time. Integrate force with respect to distance, position, right? And you're going to get a slightly different number. Related? Oh yeah, because isn't the work related to the speed, which is related to the momentum? Yeah, so, I mean, yes, they're kind of all tied here together, but they are different ideas, different quantities. And so work and energy is different than momentum. They both have their conservational principles, and they both have their strengths and weaknesses, and that's what we need to learn to see how we are going to solve a particular problem. Do I solve this problem with Newton's laws? Do I solve this problem with conservation of energy? Do I solve this problem with conservation of momentum? Linear momentum. Do I solve this problem with conservation of angular momentum? Okay, which is about as far as we'll get this semester. Oh no, then we'll get to a little bit of Archimedes' principle. Do I solve this problem with Archimedes or Bernoulli's principle? But that's going to be the end of this semester. But as we go into next semester, then do I solve this by Coulomb's law? Do I solve this by Gauss's law? Do I solve this by, and by the time we spend 3 semesters together, you're going to have a lot of how do I solve this? Is this a thermodynamics problem? Is this an optics problem? Is this a mechanics problem? And then when you narrow it down to, oh, no, it's a mechanics problem, then, okay, do I solve this by Newton's laws? Do I solve this with linear momentum? Do I solve it with angular momentum? And so our puzzle gets more complex as we understand the world more and more. And so that's always a tough decision. Which approach are you going to take? Well, that's kind of a sidetrack here. I just kind of wanted you to see that this is this integral here. Oh, how would you define, say, an average force? I mean, wouldn't you say that there's kind of a no contact, no contact? I mean, let's just say this is the baseball. No contact, no contact, boom, huge contact. No contact, no contact. Wouldn't this impulse be the same as some average force over some longer period, right? And so let's look at some calculus that's going to become important to us that maybe you've never seen before. How would you define an average force kind of in this picture? And maybe I'll backtrack. What if you guys all took a test and said, how would you get the average in this class? What are you going to do? Well, take your score plus your score plus your score. Would that up everybody's score and divide, right? Okay. So if this is some time period from, 0 to t naught, how would I think about the average force? Wouldn't I take the force, add it up, add it up? Is that an integral or am I adding it up? Well, isn't it the same thing, right? Isn't the limit as delta x goes to 0 of the sum of some f of x delta x equal the integral of f of x dx? Isn't the integral a summation? It's the whole reason we use this s for sum. Okay? And as I said before, and we'll say it again, and you'll see it more so in the next couple chapters, a big lesson this semester is, could you come up with the equation on your own? Could you think about what's being asked and then come up with your own integral or derivative based upon what's being asked? Why does delta x? That's the definition of an integral. I mean, now we can get back into our calculus and say, where did this come from? But this is our definition of an integral. An integral is a Riemann sum. Then you're taking the sum of all of these things as it gets smaller and smaller and smaller. You probably did it in terms of your calculus class, maybe something like this, and you said, here's a function f of x, and how do I get the area under the curve? And I take the value of the function and then multiply it by some width. Value of the function multiplied by width. Add it to the next one. Add it to the next one, the next one, the next one, and the next one. But I would need to make sure that I take my rectangles and make them smaller and smaller. So it's the limit as delta x goes to 0, the sum of the product, that would be the area under the curve, and that is our definition of an integral. So it's our definition here is a summation. All right, so that's what I wanted you to see. I would take the force, I would add it up for a period of time, then I would divide by that period of time, right? And that might be new to you, taking an average using calculus, as opposed to your score plus 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 your score, and then divide by the number. So that is how you learned to do averages back in 3rd grade, right? Or 4th grade or 5th grade, wherever you learned your first statistics. What is an average? And so now as we go a little bit further here into our calculus, this too would be taking an average. And here's what's kind of nice about that. If you then move the time over to the other side of the equation, then this period of time multiplied by some average force is then equal to the change in momentum. And so don't be surprised if there's a problem, something like this. Oh, a person on ice skates skates into the wall, comes to a stop, and falls on the ground. What is the average force on the person? And what probably happened is while the person is pushing on it and comes in contact, the force probably looks something more like this. They first make contact and the force increases up to some maximum, and then they kind of push away and it goes back to some minimum. So the actual equation for the force is pretty complicated. So without getting into the details, what we could say is, isn't there some average force over that period of time? And what's interesting is I don't have to know all the details about the force. Couldn't I get the force by number 1, how much time did it take for them to stop? And then number 2, what was the change in momentum? What was the speed before they hit the wall? What is the speed after they hit the wall? And so by knowing before and after, and then the contact time, I can get the average force on that person. And so what was the average force that that person experienced, or that car experienced? Okay, and that's what you're going to see here as you do the problems. It'll often ask, what's the average force? The car was going at 30 meters per second. It now crashed and came to a stop. It took 3 microseconds for this car to stop. What is the average force on this car? Yeah.
What is it?
That's well, there's nothing that would be different in this equation. But when you say comes off, now I would have, let me go this way. So then I would have, say, a positive 10 units of momentum, so 10 kilogram meters per second. And then if I stop, I would have 0. So I'd have 10 minus 0. My change would be 10. But if I bounce off, which is your question, so I'm coming in with 10, I hit it, bounce off, and now I have, say, negative 5. So what's my change? So if it's 10 coming in, bounce off, negative 5 going out, my change is 15. What is final minus initial? See? So don't think of it in absolute values. That's not what this says. And so in other words, the answer to your question mathematically is, remember momentum is a vector and it has positive and negative numbers here. Okay? So something coming in with 10, bouncing off and going back with 5 is a change of 15. It's from a 10 one way to a 5 the other way. Change of 15. So watch the positive and negatives for that. And with that in mind then, to bounce off is a larger force. Yeah. And then you can think of that in terms of the physics, because this, if I were to crash into this and just stop, you would need enough force on me from this table to just stop me. But if I bounce off, it's got to have more force than that. It's got to first stop me and then sling me back. And then that's why the 15 is used, you know, and you'll need a bigger number. You'll need a bigger force for that to happen.
I just have a quick question. The T naught equation?
Yeah?
Is that T naught? I'm used to seeing that as initial time. Is that total time?
Oh, yeah, that's the contact time. If you would like a different symbol, I'll gladly change it. But no, I don't mean initial time. This is contact time. This is during the impact, starting to hit and then stopping to hit. And the force will be some kind of complex pattern. So contact time, you know, something like that. Yeah. But yeah, not initial. Well, there is step 1. And as I said, is a different way of looking at Newton's second law. And then, like I said, it'll be the lab you do next. Not this Monday, but the next Monday you'll come in, and what we'll do is we will have something that looks very similar to this. We will then put a card on here, and we will hook a little rubber band on here, and you're going to first give it a little nudge. And before the rubber band pulls on it, you're going to say, what is its speed? And so we've got a little instrument. You're going to go through a little photo gate, and you're going to measure what its initial speed is. And then the rubber band will stretch and stretch back. Well, okay, that's this part of the equation. That's the integral. You are applying a force over a period of time. And so after this rubber band stretches and stretches back, as it comes back, you'll use that same photo gate to measure the speed now. And so couldn't you get the speed before and the speed after? So wouldn't that give you the change in momentum? And of course, this is saying that that change in momentum should be equal to the summation of the force at different moments in time. And so the reason the computer is nice is I take this rubber band and I hook it to a force probe. So when it goes like this, I will get a graph that looks something like that. The rubber band will start with a little force, and as it stretches, it will get more, and as it slings back, it will get less. And fortunately, the computer then will give me a nice plot, and I'll show you how to do it in the lab, but then we can get the area under the curve, and then the area under the curve is that integral, and so we will be testing. What was the change in momentum? What was the speed before? What was the speed after? And then we will see, does that equal to the force added up over a period of time? And so you'll the computer will measure that force for you and make a plot, and you'll have the force I think it measures the force 20 times a second. So, and that takes like 2 seconds or something. So you'll measure the force 40 times there, and you'll verify if what we call the impulse theorem is correct here. And so that's the idea here. Well, that's part of the idea of looking at momentum. And I must say, it's not the biggest part. Here's the biggest part. Here's where momentum really becomes powerful. Is what if we have more than one object? Let's start with 2 objects, and then we'll extend it to 3, 4, 5, and an infinite number of objects. Okay? But I'll start with just 2 objects. So what if I just take 2 objects, and in my case, my 2 objects will be right here. I'll call this cart number 1 and cart number 2. And it doesn't matter if, one's moving and one's stationary, or they're both moving, but it's easy for me to illustrate if one is stationary and the other is moving. What if this one comes in and hits that one? What happens right here during that impact? Yeah, if you look at, say, just this object, we'll call this number 1. As it comes in, is there a force on this cart? Yeah. Where does it come from? The other cart, right? And I'm ignoring the friction, as you guys asked earlier here. So this is a relatively frictionless surface. But I would say that as this guy comes in and makes contact with the second one is putting a force on number 1. Fair enough? And therefore, if I stop and look at this, there is a force on number 1, and it results in a change in momentum of number 1. And so number 1 here is changing its momentum. But let's look at number 2 for a second. What's happening with number 2? Does it have a force on it? It does. Where does it come from? The first one, right? And how does that force on the second one compare to the force on the first one? That's Newton's third law. So as the first one comes in and applies a force to the second one, we can look at the second one and say, wouldn't there be a change in momentum of the second one? And the force is, of course, the same as the force from the first one. So don't these 2 objects have the same amount of force on them? Opposite in direction, but same amount? For the same amount of time? So what should we say about the change in momentum of these 2 guys? Yeah, they're equal. One gains and one loses. The same amount that the first one loses, the second one gains. And that's our conservation of momentum. That is a very powerful tool. If I write it out this way, it would look something like this mathematically. I would have cart number 1 coming into cart number 2. Okay? As cart number 1 hits cart number 2, we say that there is a force. I want to get the same notation as your author, which he put from 1 onto. Yeah. And so there would be a force on number 2 coming from number 1. So it's from number 1. And then likewise, as this one is making a collision, there is a force from number 2 on number 1. And as you guys correctly pointed out, the force 1, 2 is equal but opposite to the force 2, 1. That's Newton's third law. And so if we put that, Newton's third law, together with really Newton's second law, which is this, watch what happens here. You would say, all right, what is the change in momentum of number 2? What is the change in momentum of number 1? Well, number 2 would be force 1, 2 integrated with respect to time. Force on number 1 would be force 2, 1 integrated with respect to time. If we add those together, the change in momentum of number 1 together with the change in momentum of number 2, that is the integral of F21 dt plus the integral of F12 dt. But as you told me with Newton's third law, that 1, 2 is the negative of 2, 1. And so this becomes the integral of F21 minus F21. And that is 0. And so this is what, you've been exposed to before. I don't think we did it at all with any calculus in 102, but looking at it in terms of the calculus and looking at it with the forces being equal and opposite, we get what we're now going to call conservation of momentum. What is it saying? Well, whatever momentum is lost by one object is gained by the other. I like to write it in the other form of the total momentum you start with equals the total you end with. Watch, let me keep going through the math, because then it looks a lot like what you saw for conservation of momentum. You have the change in momentum of number 1 plus the change in momentum of number 2 equals 0. To calculate a change, you would say, what is the final momentum of number 1 minus the initial momentum of number 1? To get the change in momentum of number 2, you would say, what is the final momentum of number 2 and what is the initial momentum of number 2? If you take these two negative ones and move them to the other side of the equation, you then have the way that I prefer to think of it, although of course they are the same, is to say, there's my conservation of momentum equation. Take the momentum you start with. Now when I say the momentum, what I mean is both objects here. Okay? Just like the last chapter where we had conservation of energy. Take the energy of your system. So if we had two objects, we had to do the both kinetic energy, and we had to do all the energies. This I think is a little bit easier because there is no such thing as different momentums here. This is just the linear momentum, the one momentum, but you do have to do it for every object. So take the momentum of the two objects that you start with, and guess what it's equal to? The momentums that you end with. End of story. What if I had three objects here? How would this change? Yeah, it's going to come out to be the same, no change in total momentum. Although, what could happen is with a third object, the force on this one could be made of a combination of those two, so my equations look a little bit longer. I have the change in momentum of number 2 would have two forces here because they would come from the two objects, and the change in momentum of number 1 would have two forces, and the change in momentum of the third one would have two forces, but that's a total of 6 forces. But isn't the force on number 2 from number 3 equal but opposite to the force on 3 from number 2? And so if you listed all these forces, you listed what is the force from number 1 on number 3? What is the force on from number 2 on number 3? What is the force? Well, let's make a linear list here. What is the force from number 1 on 2? What is the force from number 3 on 2? What is the force from number 3 on 1? And what is the force from number 2 on 1? Did I get them all? Okay. And as you add these all together, granted your math and your equations would be longer, and you wouldn't have something quite as short and sweet as this, but what would you say about those two forces? Equal and opposite. So they would add to 0. And then what would you say about 2, 3 and 3, 2? Yeah, equal and opposite. And those two, equal and opposite. And so by the time you add up all of these forces, the total force is going to be 0. And so with 0 as our whole force of our system, and so there we are again, just like we did our energy here, we need to look, what is our system? But looking this as a group, looking at this as 2 or 3 or 4 objects together, what's really nice is if there's no other outside forces, what can we say about the momentum? Doesn't change. And that's our principle of conservation of momentum. And I know you saw it in 102. Not quite this complicated mathematically, nor quite this complicated in the kind of problems we will do this chapter, but it's the same basic principle. I do want to point out though, what was real important for conservation of momentum here to work? What if there had been some friction here? What if there had been some other outside force? Yeah, then let's say the ground, you would have a force from the ground on objects 1, 2, and 3. But you wouldn't have the equal and opposite part of it, right? So outside forces then are going to end up changing our momentum. Okay? And so it's just like our conservation of energy. I'll put it over here. Didn't we have the initial kinetic energy plus the initial gravitational plus the initial spring plus and then outside stuff? And as long as we didn't have any outside stuff, then it had to equal to final kinetic and final gravitational and final spring and heat that was created. So without any outside influences, we could say all the energies you start with equal all the energies you end with. And we're trying to say the same thing here. So that hopefully it's easy to learn. We're trying to say that all the momentum you start with, even though the objects may gain or lose energy, but if one, momentum. If one gains momentum, the other one must lose it, right? And so the total remains unchanged, as long as there's no outside influence. So at this point, I have not included an outside influence. We soon will. So what if there is an outside influence? But building up to this, if with no outside influence, what we're saying is the initial momentum is equal to the final momentum. Okay? And so that's our conservation of momentum. Well, maybe some abstract examples would be very useful here. I think it is here. Let's look at a couple here. Let's look at one that maybe does this. This is probably the simplest one to kind of write out and analyze. What if it does this? What if we start off with the second object here not moving, but this one moving? And it comes along, and in this case, hit and stick together, and then the two move on. Could you tell me the speed after the collision compared to the speed before the collision? And I bet you probably even could tell me without even doing the math, although I do want to do the math and start with an easy one and get harder. What is that speed? It's half, right? Why would you say half? Yeah, to get the same amount, and that's the key, to get the same amount of momentum. You have just applied conservation of momentum. To get the same momentum, you said, I'm going to cut the speed in half because I just realized the mass doubled. And momentum is mass times velocity. And so sure enough, if we come over here and we put it into this equation, that's what we'll get. We can look at the first object. The first object would be mass times the initial velocity. The second object is at rest. So its momentum would have been 0. Over here, the objects collide and stick together. So you would have said mass times the final speed plus the second cart and its final speed. And maybe I should have emphasized, because I don't think I told you, these are the same carts, so the m's are the same, so I'll make no distinction there. But the real key to this then mathematically is right here. Wouldn't the speed of each of these carts be the same since they are hooked together? And again, there's one of those situations where you need to be watching and paying attention to the physics as you are doing the math and understanding, you know, reading the math. It's like, wait a minute, what do I know from the physical picture? Because you can't solve that anywhere in the math. You got to say, what happened here? And so this one right here, which was 0 speed and 0 momentum, I got from the physical picture. And then this one here that is saying it's the same speed, I got from that physical picture. They are stuck together. They are going the same speed. But then once you do that, then you've got a 2mv final is equal to mv initial. The m's cancel off. And if we then solve for final speed, we do mathematically get what you very quickly and obviously told me, is that the final speed is half the initial speed. Sure, half the speed, because we've got twice the mass, right? And so our conceptual solution as well as our mathematical solution agree. Let's try another one. Not much harder than that one, but a good first step. What if I turn it around so the collision looks a little different? Again, I will start with this one at rest and this one moving and collide them. And now they don't stick together. It's a little different scenario. They look like this. So what is the speed of this second one after the collision in comparison to the first one before the collision? Is it the same speed? I agree it is. And why do you say it's the same speed? Yeah, see, you're looking right away at the conservation of momentum. You're saying, look, I'm looking at this saying, this guy's moving, this guy's not. Before the collision, all the momentum is with this guy. And as I watch it, this one stops. This one has no momentum. So what must this one have? All of the total momentum, right? And it has the same mass, so therefore it must have the same speed, right? Let's try the math. The math should give us exactly the same thing. And so if I come over here and I look at this equation, I would say, all right, let's look at the initial momentum of the first one and the second one. So there we are again. The second one is 0. I got from the physical picture. Jump on over to the other side of the equation and I'd say, okay, what is the final momentum? And in this case, looking at that physical picture, I noticed that the first one stopped. Okay? And so how much momentum do I give? 0. And then the second one starts moving, so it would be mv final. And so the math here is a little bit easier than that math. I didn't have to combine anything together. I just come up with the initial speed equals final speed. Right? All right. Should I make it go harder? I'll turn it around again so they stick. This bar has the same mass as each of these carts. So I will put one on this car, the first one that's moving. If I can get it in there. And I will stick them together. What's the speed after the collision? Same as the cart. All right, so it is a little harder to do that one mentally, but some of you have got it figured out. Let's go through the numbers here. Let's go through the equation. So I'll start here with the first one that's moving. I guess I would write that as 2mv initial. Fair enough? Plus the stationary one again. So far I've always given you a stationary one, but maybe we should let the other one move now, right? All right. Now I come over to here and I say, okay, now what happens on the other side? Well, the first one has some final speed. And the second one, and that's the key to this problem, which makes it a little bit easier, the second one is hooked to it. So don't the two have the same speed, whatever that speed is? And so this comes out to be 3mv final. This is 2mv initial. M's cancel off. Solving this for final speed, and final speed then is 2/3 of initial speed. Okay, so it'd be 2/3. I heard some of you say 2/3. I heard some of you say 1/3. Be careful, you were thinking probably more along this lines. Had the mass bar been over here and it collided, that would have been 1/3. because this side would have been the same, but that would have only been a 1, and so that would have come out to be 1/3. Okay. So a lot of different combinations that could occur, right? So let me just kind of move away from this for a moment and say maybe we should write this in general. So here's the equation in general we're going to do, and this is what your author does in the first couple of sections here. He says, let's just put two objects, call it object 1 and object 2, and each of them will have an initial speed and each of them will have a final speed. But in general then, the equation should look something like this. m1 times the initial speed of number 1 plus m2 times the initial speed of number 2. Well, let me pause there. Do you see where I got that? What is that? Isn't that this right here? Initial momentum of the first one and initial momentum of the second one, where m1 and m2 are the mass of 1 and 2 respectively, and initial velocity 1 and initial velocity 2 are the initial velocities of 1 and 2 respectively. So this is a much broader problem where I can have any masses and any velocities, right? That equals what? Well, m1 final number 1, right? And m2 final number 2. And so this is what this equation comes out to be. The momentum before equals the momentum after. Now if you think about this, this problem in general has how many unknowns? Well, I guess we would have the masses of the objects, so there's 2, right? And the initial speeds of each, there's 2 more. And the final speeds, right? There's 2 more. All right, so really as I look at that equation, there's 6 unknowns there, right? Now a typical problem is usually something along this line of initial conditions. In other words, here are 2 objects. Mass of this, mass of the second one. The first one is going this speed, the second one is going that speed. And then they collide. What is the speed of each of them after the collision? Can you solve that problem with just this information? No, why not? Yeah, I need one more piece of information, don't I? If I gave you the initial conditions, I'm only giving you 4 things, right? I'm giving you the mass of each object, the initial speed of each object. I need another piece of information. Don't you need to know 5 before you can solve for the unknown? All right. So keep that in mind, that although we've had this long discussion, this by itself is not enough. They need to tell you something more, okay? And maybe that would be the final speed of object 1. Or maybe it would be they stick together, right? Or maybe it would be watch it and the second one starts to move, but the first one stops. So there has got to be some additional piece here. And I've shown you those where they stick together. That was my additional piece. I've shown you where they don't stick together, but the first one stops. But in general, I could not do this problem. What if I put mass on here? And turn it around and say, well, let's give this a little speed and this a faster speed. Let them collide. I can't tell you exactly their speed. I need one more piece of information. And there is one more that we haven't even mentioned yet. I did mention that stick together. Okay, you saw that one, right? I did mention that and watch you say, look at it, stop. But it really goes back to last chapter. What else is going on here? What about conservation of energy? You haven't forgotten about it, right? Doesn't that have to also be true at the same time? So, don't forget that 1/2 m1 v initial 1 squared plus 1/2 m2 v initial 2 squared has to equal 1/2 m1 v final 1 squared plus 1/2 m2 v final 2 squared plus any heat that might occur in the impact. And so there's our conservation of energy from the last chapter. Now notice there's no springs up there. So, I mean, we could make this harder and put springs between them also. I don't think we do any of that. You know, that's a little beyond where we're trying to go this first semester with you. I guess we could also make it go uphill, and so there would be a slope to the hill, but you know, let's not worry too much about that. If you could do this much, then that's the idea. My point is, don't forget that not only is momentum conserved, but energy has to be conserved. But, for better or worse, didn't we throw another unknown in there? Assuming there's no outside forces, there wouldn't be another term here. But these equations almost have the same unknowns. There is one more, the heat, right? Now I should be careful here because this heat's a little different than what we talked about last chapter. Last chapter, when we had a block sliding on a rough surface, where was the heat? But from the friction. When I have a collision here, where's the heat? Yeah, and so remember, we are still talking about no friction down here on the table. So why would there be any heat? Yeah, where they collide together. And so when these come together, boom, right there, there's rubbing of molecules. So cart 1 hits cart 2 and make those molecules go faster. So when I say the heat, I'm not talking about a heat here. I'm talking about the heat of the impact. How does one molecule, where does some of that energy go? Okay. So this is your answer in general. And maybe this is too general to kind of discuss, but it really helps to look at this. For example, maybe I'll start with this one here. This is one of my favorite ones here because this was the one I did second. And maybe I should redo it again. This is the one that had equal masses and they did not stick. It went like that, right? Now, the reason we could solve it without even thinking about this equation was, what was my added information when you watch this? Yeah, that one stopped. And so as we worked it out, we said, all right, the first one is moving, the second one is stopped as we got started. Then they made a collision and the first one stopped. That was that extra piece of information. I go to solve it and I say, look, this is my answer. My speed of the first one equals my speed of my second one. But let's take that and talk about energy now. How would that equation work out here for energy? Well, first one would be a 1/2 m1 v initial 1 squared. And the second one would be 0 kinetic energy, right? Then they collide. What's the kinetic energy of the first one? 0. What then is happening with the second one? So this would be the kinetic energy. But wait a minute, what did you say about the velocities of these two guys? Didn't you say they were the same? Right? Isn't that the information we got by conservation of momentum? So in this case, I'd say, I can say those are equal. And so what do I come out with for Q? And so what is all this math telling me? I mean, I did it great. What does it mean?
There's no heat.
Yeah, there's no heat created in this impact. In other words, the kinetic energy before the collision equals kinetic energy afterwards. Is that always going to be true? No, look at the first one I did, right here. Remember this one? Let's try that same up here and do it again. So maybe I'll put a little dividing line here between that calculation. Let's look at this first one. Now, if you remember the first one, let me set it up again. This first one looks something like this. It's where this one was moving and the Velcro. That's the key. Did these cars touch? Did one molecule hit another? And that's going to make the molecules start going faster. Isn't that what heat is? You see, the one I did where they don't actually touch doesn't make any heat. And so there was no heat created. But as soon as I turn them around and get the magnets away from each other, and the two have now, it's going to make these molecules and these molecules go faster on that impact. And so are you going to get some heat created? Yes. And so is the kinetic energy before the collision going to equal the kinetic energy after the collision? No. But wait. Did the momentum before the collision equal the momentum after the collision? Yes. And so collisions like this have no heat generated. Collisions like this do have heat created. But don't both of them have conservation of momentum? Please remember that. You always have that conservation of momentum. We like to give a fancy name to these guys. These guys that don't have any heat, we like to call them elastic. We like to say, okay, this is an elastic collision. No heat is created in there. If some heat is created, maybe I'll put it over here. So if Q does not equal to 0, we like to call these inelastic collisions. And so this word elastic and inelastic are going to be very important to you as you do the problems. If the author goes through and says two cars or two billiard balls or two molecules have an elastic collision, they just told you something very important, right? They've just told you Q is 0. Don't overlook that. Or if they tell you it's inelastic, what have they told you? There is a Q. It does not equal to 0. Don't overlook that. But I will say that I think one of the common mistakes, so let me give you a warning here, is students somehow associate elastic and inelastic with momentum. And that has not to do with momentum. Was momentum conserved in the elastic? Yes. Is momentum conserved in the inelastic? Yes. The conservation of momentum is true regardless of the elastic or the inelastic. That's not what we use the word for. The elastic and the inelastic is telling us something about how much heat is created here, how much energy is lost during the impact. And maybe lost is a bad word. Lost from kinetic energy going into, and I said heat, but the truth is it could be also in other forms. It doesn't have to be into heat. It could be compressing a spring. The energy went somewhere else. It could be in deforming metal, as often happens in car accidents. The piece of metal's here, and now you applied energy to it, and the energy is now stored in a spring, if you want to call this a spring, but it's stored in the deformation of that piece of metal, the changing shape of that piece of metal. And which then, because of the molecules, could turn into heat there too, but let's not quite go down that road here. But as I started to do here, let's then do the calculation for this one. And I claim this is an inelastic collision. I claim that there will be a Q here. Okay? And what made it possible for us to solve this one is we knew that the velocities have to be the same. They stick together. So as I write out my equation, I guess I would start the same way and say, all right, here's the first object, and there's the second. First object is moving, second one is stationary. Then they collide. And when they collide, I get 1/2 m1 v final 1 squared and m2, which is v final number 2. Oh, I'm sorry, well, what should I put here? Should I put 2 to get started with? Well, no, then it's just that equation. But I guess that's what I'm after. That because they stuck together, I know that these two speeds are the same. And there's really no point then in calling it number 1 anymore. It's just what is the final speed. And that's what I did over here. I said, look, they stick together, so they have the same speed, v final. And now, as we work out our mathematics here, we can write this as a 1/2 Well, let's see, how many steps should I take here? I don't want to lose you, but I don't want to start erasing things quite yet. But if these two masses are the same, then the 1/2 and the 1/2 add together to give me a 1. Fair enough? And then the final speed, I know from over here, the conservation of momentum, it's half the initial speed. So I can put in the initial speed divided by 2 and square it. Oh, yeah. Well, in general, they are different masses. But for this problem, right here, for this problem, they are the same mass. Okay? So general, and then specific here where it was elastic, and specific here where it's inelastic. But I do want you to see then that this number here does not equal this number here, does it? This number is a little bit smaller than that number. So some of this energy went to here. And so as I finish the equation, Q then equals 1/4 mv initial squared. Which, if you want to think of it as 1/2 of the original, that's the original, that's 1/2. You're saying half of the energy went into heat. And so I'll say lost, but I always want to be careful with that word. You can never lose energy, but you transformed it from kinetic energy into heat energy. And so there was some heat created here. So I want to emphasize it again. Momentum was conserved. Kinetic energy was not. Total energy was conserved. So we have conservation of momentum. We also have conservation of energy, but we have lost kinetic energy. Some of the kinetic energy is shown up as heat. So sometimes you don't create any heat, sometimes you do. And in this case, 50% of it is created as heat.
Yeah, that makes sense to me, but if the velocity is a little bit smaller, the final, right? Because some of the energy went into the heat.
Okay.
Well, isn't momentum mass times velocity, and so a little bit of the velocity is lost? How is not a little bit of, I mean, I guess momentum's not lost, but I'm saying that, you know what I'm saying?
I think you're getting at this, that, okay, wait a minute. We lose kinetic energy, but we don't lose momentum. How is that possible? Well, it lies in the mathematics of, notice that for momentum is mv, but kinetic energy is mv squared. Okay? So, when velocity goes from, say, a 1 to a 2, this number doubles. But when velocity goes from a 1 to a 2, what happens to here? It goes from a 1 to a 4. So the effect of velocity is different on the equation for kinetic energy than on the equation for momentum. And so that's why you could still have momentum being conserved, but yet kinetic energy is not. Because in this case, what happened is we changed our velocity in half. So we got half the velocity, but we doubled the mass. And those two balanced each other. Half the velocity, twice the mass. But over here for kinetic energy, when we cut our velocity in half, our kinetic energy goes down by 1/2 squared. So our kinetic energy goes down a lot more because of the square. And so even though your velocity squared goes down by 4, your mass still doubles, but the 4 doesn't balance the 2. But over here for momentum it did. Your mass doubled and your velocity cut in half, and those two balanced each other. But it doesn't happen when you have velocity squared. So so there's the answer. Okay? And in fact, I can tell you this, that anytime the objects stick together like this, there is no way you could also have Q equals to 0. Because you can see it in the math that your velocities are going to be the same. You can't have them the same here, one doubling and balancing the other one, or tripling and balanced by the other one, and have the same mathematical or a different mathematical relationship and get the same balance effect. So anytime the two objects hit and stick together, you're going to get some heat. Guarantee it. I mean, that's hopefully pretty clear in the math. It's also hopefully pretty clear just in the physics. If they stick together, don't they make contact? And it's that process of pushing on each other that is where you are making the kinetic energy turn into heat energy. And so anytime they stick together, definitely going to be heat. So we have one more word. Besides the word elastic and inelastic, we have the perfect inelastic. And that perfect inelastic is really saying the final speed of 1 is equal to the final speed of 2. And so that's what we call it when they stick together. So careful when they say that. If they say perfectly inelastic, or perfectly inelastic, what they are saying is they're saying they're going to stick together. And also, when they say that inelastic, they are saying there's going to be some heat created here. Okay? Now, how long has I taken? A little more than an hour here, but let me just recap here. Because this chapter, I think, can get lost in the details of working out conservation of momentum and working out some problems. But here's what I want to say. You have now this idea that the initial momentum added up of all of your pieces. Because didn't I only do 2 pieces? Could this have been a collision with 3, 4, 5, infinite? Ooh, infinite would be fun. How are you going to handle infinite? Adding up an infinite number of momentums. An integral. Of course. I don't need to be told that. All right, so we can start adding up our pieces. Okay, they can be 1 or 2 or 3 or an infinite. Okay, and we soon will add up an infinite number of objects. But here we will add up, and I'll just put it in a symbol like this. Maybe I should ask, you seen this symbol? A little, guess it's not a very good drawing here. But that's the sigma. Oh, I guess I used it back there on the definition of the integral anyway. But it's the summation. It's the capital sigma from the Greek alphabet here. But it means add up all the momentum. So add up all the initial momentums. And then what does that equal? Yep. That has to equal all the finals. And so that's what I'm saying. Whether I put 2 objects or 3 or 4 or 5, whether one object is moving or not, whether they're both moving, whether one's moving to the left or to the right, do you see the idea how many problems we can have? Tens of thousands, if not hundreds of thousands, if not hundreds of millions of different combinations. But the principle is the same. The fundamental principle, and that's this whole idea. What are the simple, fundamental, powerful ideas that explain what's going on? And conservation of momentum is one of those. And so that's the first half of the chapter, if you will. Now, don't forget, though, to include that with initial energy is equal to final energy. And so that's the second piece of the puzzle that I was trying to add on here. Sometimes, you know, the problems are pretty complicated, and they, you know, they'll have to tell you things like, hey, no heat is created. You know, they'll usually say that by elastic collision. Okay, none of the energy goes into play there. And that second piece of information can often be needed, you know. Or they just say they stick together, and then maybe you don't need this piece of information. Or maybe you do need that piece of information. In fact, let me go one step further, because so far, not only did I just talk about two objects, but they were going in a straight line. Isn't this a more complicated world with 2 and 3 dimensions? So, what if instead of having these two carts, I had, and I hesitate to use two pool balls, but they make good examples. The only problem with pool balls is, in addition to moving, they roll. And we haven't done any rolling yet. And if they roll, then we have to talk about the interaction of the felt with the ball, and then we have to talk about angular momentum. So if we forget all of that, and maybe just say, here's 2 pool balls on ice, 2 hockey pucks, you know, on ice. That's why it's hard here. I mean, you know, we don't even know what ice is, let alone hockey, right? Okay. 2 shuffleboard discs, which is such a common game. I know you guys know what shuffleboard is, right? Right, and those 2 discs, it's like in the Olympics, those big discs. Curling. Curling, oh yeah, and I'm sure that was top on your list of, you know, winter sports, you know. All right, so it's a little hard for me to give some really good examples without talking about the pool balls, but then the pool balls are a little too advanced for where we are right now. But imagine 2 objects coming in. A bullet in a can, maybe that's the best one. A bullet hits can, right? What happens? Yeah, that'd be a big bullet, right? Yeah, and so what ended up happened is this first one may ricochet and go off that way, and this one may ricochet and go off that one, right? So they don't just move in a straight line, right? It's a 2-dimensional problem. But I want to say, it's the same way. It's just a vector. See, what really is meant here? Well, I guess what is really meant in that equation is the initial momentum in the x direction is equal to the final momentum in the x direction. And the initial momentum in the y direction is equal to the final momentum in the y direction. Does that make sense? There's really another equation in there. Don't overlook it, because you probably will need that other equation, right? How do I solve for that other equation? Now, my third equation is still initial energy is equal to final energy. So here are my 3 equations for this kind of 2-dimensional collision that's taking place. Now again, just like I was showing you the last half hour here, is there's all kinds of combinations I could give you. I could start with the first one moving and the second one at rest. Or they both perhaps could be moving. They could collide and stick together. They could collide in such a way that one stops and the other starts going, right? But there is some information we can get depending on the problem. For example, this one, I was trying to illustrate it by saying this first object, number 1, has a mass of number 1. The second one we'll say has mass of number 2. The first one then has an initial speed of number 1 this way. And this one we'll just say is at rest. So the initial speed of number 2 is 0. And as this number 1 comes by it and kind of does a side swipe, doesn't number 1 go up and number 2 go down? Could they both go up? Could they both go down? Is there any way I can make both of them go up?
Well, what do you hit it? The force is going down.
A light one hit a heavy one and they stuck together. A light one that was moving hit it.
So if they stick together, could I make them both go up? If this one was heavier than that one, could they both go up? If this one was heavier, could they both go up? I claim there's no way they can go up. Why not? How much momentum do I have in the vertical direction right here? 0. So how much do I have to have at the end? 0. How many ways can I get 0? If both going up will not give me 0. If both are positive, there's no way. But I could get 0 if what? One goes up and one goes down. One has a positive y after the collision. One has a negative y. So could I get them to ricochet so one goes up, one goes down? Oh, very easily. And most likely to happen. But are both going to go up? No. If they stick together, could they go up? No, because then I would have only a positive. I would have a positive after but a 0 before. It would violate conservation of momentum. Now, please remember, this is without spinning the ball on the felt, type thing. So, we could hit the pool ball like this, and then this one can have spin, and then arc around, and both of them, so I'm not talking about something more complicated than just a regular two-dimensional collision. Object 1 hitting object 2, no spin, no friction from felt, okay? But the initial impact, there's no way one or both could go up or both could come down. They would clearly violate this piece of the puzzle. Okay? So again, that's what I wanted you to see. So look at what can. These conservational principles are very powerful. They tell us what can and cannot happen, right? Can I make a machine that would produce more energy than I put into it? And hence I can go buy a gallon of gas and make 2 gallons. And then put those 2 gallons in and now have 4 gallons. And now put those 4 gallons in and have 8 gallons. And maybe I'll only keep 1 more gallon and go sell 7 gallons and take that 1 gallon and make 8 more gallons. Go sell. Can I make a machine like that? No, why not? Conservation of energy. It's telling me what can and cannot happen in the physical world. And I can't make energy out of nothing. Okay? I can't put less energy in than I get out of it. Right? I gotta put that amount of energy in to get it out. So I can't make gasoline out of nothing. I can't make electricity. Now, could I convert other energies into gasoline or into electricity? Yeah, which is the whole way we, run our world, usually on electricity. And so what we do is we take a river and we make a dam, and we take the potential energy of the water that's stored behind the dam, and we let it flow, which makes kinetic energy. We make it move a turbine, which makes electrical energy, and now we have that electrical energy, and that's how we run our industrialized world. Or we have the wind blowing, which is kinetic energy. Or we burn a fossil fuel, which then makes a heat energy, and the heat energy moves so we always have this conservation of energy. But these principles are telling us what can and cannot happen. F equals ma tells us what can and cannot happen. Conservation of linear momentum, what can and cannot happen. Conservation of energy, what can and cannot happen. Conservation of angular momentum, conservation of charge, conservation of baryon number, conservation of all these things. This is the idea of the physics. Knowing these principles, what can and cannot happen, lets you be the creative scientist or engineer to do something that hasn't been done before. It's like, how could I get X, Y, Z to happen? Knowing I can't do such and such because that would violate the second law of thermodynamics, or it would violate the conservation of energy. It would violate. So that's what I'm getting out of here. There's right away, one's got to go up, one's got to go down. Now, if I put this into a set of equations like this, and I say, okay, let's call this one of the I'll call it a scattering angle. Oh, and just to be consistent with your book, he calls one angle theta and the other one phi. And I just want to make sure I do the same so that it's in your notes that way. And I forget which way. He calls number 1 going up theta and number 2 going down phi. And maybe it's even worth asking, is theta and phi the same number? No, not necessarily. There are certain conditions that will require theta and phi to be the same number, sure. But as we write it out, let's see what we have here. I'll start with momentum in the x direction. So how much momentum do I have in the x direction before the impact? Well, I guess it would be m1 v initial 1 plus 0, right? How much momentum do I have after the impact? Well, maybe I better put some more notation on the board here. M1, M2. This would then be V final number 1, and this would be V final number 2. But how would I get the momentum in the x direction here? M1, V final 1. Am I done? No, what do I need? Yeah, it's a vector. So I got cosine there. And then how would I get the x momentum of number 2? M2, V final 2 times cosine of phi. So that would be one of these 3 equations that I could write out for this particular scenario. Okay? And obviously there could be other scenarios. Obviously number 2 could be moving. Obviously number 1 could have been, going up at some other angle. But in this case, probably the simplest one to do is just have the second one stationary, the first one moving, comes along. This would be what I would call equation number 1 for that case. But couldn't I also do the same thing for the momentum in the y direction? So, as I write out this equation, what is the momentum in the y direction before the collision? Yeah, that's a 0. It's not moving anything up or down. It's all moving horizontally. And that was our argument of why you couldn't have 2 of them going up, because then you would finish with a positive momentum in the y direction, and yet you started with 0. So now looking at momentum of number 1, what is it in the y direction? Yeah, sine of phi. And number 2, and it would be sine of phi, and it would be in the negative direction. And so again, you might want to call this equation number 2. But both of those would have to be true. Okay?
So that's for the P of P initial x equals P final, number 1.
So this one is for conservation of momentum in the x direction. And this is conservation of momentum in the y direction. And then I would have my third equation, which is conservation of energy. And so it would be 1/2 m1 v initial 1 squared, 0. Okay. For this case, and I want to emphasize, for this case, don't think it always comes out to be 0. And I don't think you're thinking that. I think you see the idea that one could have been moving. And so you've got to look at whatever is going on in that particular problem. That's why I think maybe some of the best ways of doing these is to have me do examples, which I soon will. Probably not today. We'll wait till after the spring break and do some of the examples on the next Monday and look at some of the calculations. Although it'll be useful, but I have a feeling you'll probably still be focusing on getting ready for the test then. All right, so fair enough. But my point is, these equations are getting pretty long. And there are tens of thousands of different combinations. And the only thing I can really tell you is, do you want all the answers to chapter 9? There it is, right there. There it is. Start there. And sometimes they'll hit in 2 dimensions. Sometimes one will be stationary. Sometimes they'll hit in 1 dimension. Sometimes both will be moving. Sometimes heat will create it. Sometimes it won't. Just apply for that situation. That's the idea here. All right, well, I'll keep working this out, because then this would be a 1/2 m1 v final 1 squared. Cosine? Sine? Cosine or sine? Phi or theta? Neither. It's a loaded question. This is not a vector. Okay? And it's easy to fall into that trap. You start doing these vectors for momentum, and you start doing its components, and now you go back to the energy. Remember, the beauty of the energy was it had no vectors. It was a scalar. So just put the speed squared. You're done. End of story. That's why I like, personally, to see if problems will be solved by conservation of energy first. There's no vectors. There's no components. There's no F equals ma. There's no integrals to do. So I think, as a couple of you told me, you're like, hey, this chapter 8 is a lot easier than the chapter 6 I was struggling with. And I think that's a big reason why. We're not doing integrals. We're not doing components of vectors. Okay? So if that makes you feel good, if it makes you feel sad, and you like hard problems, you're going to love chapters 10 and 11. Good. So it will get harder, okay? All right. But if that makes you sad, then you'll be glad to hear they get easier as we get into 12, 13, and 14 and finish up the semester. All right. But if that makes you sad, when we return in August, watch out. I mean, that chapter 23 is a doozy. So, I mean, that's always an interesting look on students' face. Come in, first day. They're thinking, oh, remember Physics 121? First day we did unit conversion. How many centimeters are in a meter? Chapter 1. We're right in the middle of the book. When we're at chapter 23, first day, and one of the hardest chapters. Just, wow. Didn't expect to see so much calculus on the first day. So anyways, I shouldn't tell you that yet. You might not show up after the summer, you know, disappear. Change your major over the summer. Sad. All right, well, I better keep going with this. All right, so this was me setting you up to say these are scalars. There's no sine or cosine in. But we do have the energy of the second one, because now that we've hit the second one, is now moving, so we have a kinetic energy for the second one. And since they've touched each other, there's a good chance, depending on how they touched each other, there's some heat. There may not be, if these are all magnetic, or they're what we call elastic materials, which make elastic collisions. They kind of act like little springs where they come in and they deform and bounce back on each other. Then we say there's no loss in energy. They just kind of compressed and uncompressed and pushed off each other. So we get all of our kinetic energy back. But and pool balls are designed to be that way. They're really hard, and they're designed to keep this at near zero values. I guess there is no perfect zero value, but near zero values. But that would be what I would call equation number 3. Okay? And so that, believe it or not, is most of the chapter. And like I said, really the best thing I can start to do at this point is to say we should just do examples of ones that are going on. There are so many different combinations. And the equations are so long that it wouldn't do me any good to say, hey, let's just solve this in general. Let's solve it specifically for specific problems. So, with that in mind, even though there's still more to talk about in the chapter, but with the time we have left, I will wait to talk about the other stuff in the chapter. I want to actually do some examples. Usually I wait till I talk about the whole chapter and then I do some examples. But I want to do some examples of just like this, and we got 20 minutes, so we'll do one or two and kind of set the, hopefully this into cement a little bit better. Kind of lost my list here. And I think 22 is on my list first. Yes. So here's 22. 22 says a 7-gram bullet is fired from a gun into a 1 kilogram block of wood that is held in a vise. Now, it penetrates 8 centimeters into this block of wood. Now, this block of wood is removed from the vise and placed on a horizontal surface that is frictionless. And a second 7-gram bullet is fired into this block of wood. To what depth does the bullet penetrate the wood? Will it go the same 8 meters, centimeters? More? Less? It's going to go a little less. How much less? Can we calculate it? All right. So let's use this idea for this problem. But let's start with that first step, I like to say. You got a good physical picture of what's going on. Let's read it again here. It says this. It says it's a two-step process. The first part of the experiment is you take a bullet that is very light, 7 grams, and you fire it into a 1 kilogram. That is a 1,000-gram block of wood. Okay? And I, as you'll see here, I think in the numbers they want us to see how big those numbers differ, because when we do it a second time, even though you might argue, well, where's that first bullet? It's probably lodged inside. Let's still just think of the block as being the same mass the second time. I know it's really 1,007 grams now, but for our numbers to work out, I think they want us to just say it's still 1,000. But here's the first shot. So the first shot comes in, penetrates in, comes to a stop. This block can't move because it's held in a vise here. Big old C-clamp.
Wouldn't it maybe use enough because all that extra space that the bullet took off?
Well, it depends how, right, did it come flying out on impact, which there probably is some of that, or did it just squish it in and compact it so it's a higher density, but the mass is still there? I don't know. All right, so this part of it is, you know, we don't know that part of it. All right. So you good with that? That's the first shot. First shot, right? Fires in. Let me just check the numbers here. 22, 7-gram bullet fired from a gun into a 1 kilogram block of wood held in a vise. Penetrates the block to a depth of 8 centimeters. So this distance here is 8 centimeters. All right, so now we repeat the experiment. And then this time, we place the block of wood on a frictionless surface and fire a 7-gram bullet. And what depth does it penetrate now? And so here's the second firing. We got this 7-gram bullet. Here's our block, and I'm going to give it 1 kilogram again here. And as it goes to penetrate, something different happens this time, though. What happens? Block starts to slide, right? Starts to move, which kind of makes you feel like, hey, it's not going to penetrate as deep. Oh, exactly. And the question is then, how much less? Well, wouldn't it have to do with how it's moving? It doesn't have it moving have to do with the fact that it's frictionless, which has to do with the momentum? Absolutely. That's why it's in this chapter, right? We can work this out. So maybe I'll start here with this problem. First of all, this one, it's important to realize that aren't there outside influence, this clamp? So is the momentum before equal to the momentum after? No. Because there's an outside influence? And so maybe I should pause and go back to our derivation. Remember our derivation of conservation of momentum? Didn't I have 2 carts? Cart 1, cart 2. And what we said is cart 1 put a force on cart 2, and cart 2 put a force back on cart 1. And so we said as long as there was no friction down here on the table, there was no other forces. And when we have our system with no external forces, those will all add up to 0. That's the only way you can get your conservation of momentum. So be careful as you set this up and as you look at the problem. Are there any outside forces? If there are outside forces, you're not going to get your conservation of momentum. And I think you see that here. Before the bullet hits, isn't there a lot of momentum? Now it impacts, stops. What's the momentum? 0. Isn't there a change in momentum? Oh, absolutely, right? And it's all because of the clamp that is holding it into place. Because what's different in part 2? Is there a clamp? Is there any outside forces? No. There's no friction. That was the key to it. No friction meant No outside force, which means we can use conservation of momentum. So in part 2 here, we can say the initial momentum, and it's only in x direction, we can say the initial momentum in the x direction is equal to the final momentum in the x direction. That is true for the second experiment. It is not true for the first experiment. So that's one of many reasons why I picked this one, is to just kind of recap the derivation. Make sure you set up your system correctly. Make sure when you go to apply conservation of momentum, you remember that I need to be looking at a system with no outside forces. Okay? And so this one has outside forces. This one does not. This one I can do conservation of momentum. This one I cannot. But what about conservation of energy? Okay, that's conserved, and it would be true in the first experiment and also true in the second experiment. So let me write initial energy is equal to final energy. Let me also write initial energy is equal to final energy. So as I go to apply these two principles, conservation of energy and conservation of momentum, to these two experiments, what do I come up with? Well, let's do the energy to this experiment. What energy do I start with? And when I say start, I guess we're back to, this whole idea of chapter 8. What do you mean by initial? And I mean right before the impact. So I'm not talking about before the gun is loaded and before the firing person was born and before, all that. I'm talking about right before you make impact. What kind of energy do we have? Kinetic, right? So I guess I'd write this as 1/2 mass, and I'll put a little b here for bullet.
Is this for the first one or the second?
Yeah, the first one. So let me draw a line. Okay, so this is the equation applying to the first experiment. These are the two equations applying for the second experiment. That's what I'm trying to find. How far does that bullet get lodged in there? So it'd be 1/2 times the mass of the bullet times the velocity of the bullet squared, right? Where does that energy go? It all goes to heat, right? That bullet makes impact. As it's penetrating in, molecules are hitting. They're now going faster. This thing's in a vise. There's no kinetic energy. There's no springs involved. There's no potential energy. All the energy goes to heat, at least in that case. And heat would be calculated as the force of kinetic friction times the distance traveled. And how far did it travel? The 8 centimeters. So this is how I would apply conservation of energy for the first experiment, and I would not try to apply conservation of momentum because it's held in place with a vise. Fair enough? Look at the second experiment. In the second experiment, I can do the momentum one as well as the energy. But since we're already talking about energy, can I do this one first? All right, so let's do this one first. 1/2 times the mass of the bullet times the velocity of the bullet squared. So that's still the same, right? That's the kinetic energy before it makes impact. Where does that energy go? Yeah, is there any heat created? Yeah, does all of it go to heat? No, why not? The block starts to move, right? And we know it has to move because of conservation of momentum. So I would put 1/2, and then I'll put maybe, how about, can I do a capital M for the wood? Okay. Now you could at this point say it is either 1,000 or 1,007, or I guess even 1,014 by this point because we've shot 2 bullets in it. So maybe we should decide that later on. But this is the target, if you will. This is that big block of wood plus maybe 2 bullets. And then it's the velocity of the wood squared and, as you said, heat. And how do I calculate heat? Force of friction times the distance traveled. And now is it 8 centimeters this time? No. And so there's the part that I am looking for, that x. How far did it travel? So this is what I would really like to find out. Now, let me also do this one here. What's this one? Well, What's the momentum before the impact? Wouldn't it be mass of the bullet times velocity of the bullet? What's the momentum after the impact? Wouldn't this be the mass of the wood times the velocity of the wood? And that's really the key to this. Watch as this plays together. If you apply both principles, conservation of momentum and energy, and then up here just energy because we couldn't apply conservation of momentum. But if we put these three things together, we should be able to solve for x. I will take this equation and start to write it out. I'll start with right here and say, you see this one? 1/2 mass of the bullet, velocity bullet. Isn't that the heat from the first one? Which is the force of friction times the 8 centimeters. So I'm going to put force of friction times 8 centimeters. Although I guess I'm writing in terms of meters. Okay? And so I've replaced that one. Let's try this one here for a second. What's this one saying? Well, this is the kinetic energy. But isn't the velocity of the wood related to the velocity of the bullet? So let me do that substitution. So this is 1/2 times the mass of the wood times, and in place of the velocity of the wood, let me put mass of bullet, velocity of bullet, divided by mass of wood, and square it. So isn't that what this is doing here? Plus force of friction times x. That one, right here. Velocity of wood equals mass of bullet, velocity of bullet, divided by mass of wood. Okay. So I'm going to solve this one for velocity of wood. I'm going to put it into here. Now as I do a little bit of algebra, this becomes 1/2. And this would become mass of the bullet squared. This would become velocity of the bullet squared. This would have a square which would cancel with 1 up there, so I would just have velocity of wood there. And then this would be force of friction times x. If I rearrange this equation here, I can write it as mass of bullet over mass of wood. The 1/2 mass of bullet, velocity of the bullet squared, because, you know, this comes out, but this looks very familiar because it's that. And so I will do that substitution in a second. And so using that substitution, I will take the mass of the bullet divided by the mass of the wood. And then that is my substitution from this again. I did it one time here, but I'm going to do it a second time and write it then as force of friction times 0.08. Lucky for me, force of friction shows up in every term because I don't know what that is. But of course, that's why it came up with the 8. So, you know, that's how the 8 is related into here. And so what I eventually get here after solving my math is x equals, and I'll move this to the other side, it's 0.08 minus mass of the bullet over the mass of the wood times 0.08. And so now I can answer that mathematical question. How far did it go? So it's 0.08 minus, and if we take the bullet at 7 grams, and we take the wood, then I guess here's my question. It's 1 and what? Do you want to do 14? Why not? I guess we fired the first one in there, and then we fired the second one in there, so okay. So it's 1,014 times 0.08, that would be my x. Now, I'll admit there's a lot of algebra here. There's a lot of math here. There will be for this chapter. Okay? But, and I'll help you with the math if that's a problem for you. But that's not the intent of my lecture. That's not the intent of this class. The intent is, you see how I did it? You see how I just wrote down a very powerful, fundamental equation? And I solved for this? And that's what we're going to see again and again as we do this one. So, one final step here, I guess, 0.08 minus 0.007 divided by 1.014 times 0.08, coming up with 79. So, didn't change by much. Pretty close to an 8. But again, not worried about the actual number as much as the logic behind it. So, all right, well, we'll stop there. Have a good spring break and a safe spring break. Okay? I've taught here for 17 years and there's never been a spring break where somebody doesn't come back on crutches or a wrist guard or something. Although the worst case scenario, I won't even go there. So 4 days in the hospital.